And hi, welcome everyone to this video. Today we're going to talk about natural convection boundary layers. So last time we talked about forced convection. Now let's move on to natural convection. Okay. So where do we start? We start out from our basic principles again. They are the usual mass, energy, and momentum balance. So yeah, for now I have some of my notes written out. It's sort of faster and smoother. Okay. I did some of the work before that. Rather than type everything out, I may still type some equations out as we go along, because not all of this is complete. So we have a mass balance, continuity equation, momentum equation, energy balance equation. Okay. Of course, remember these actually have the assumption of incompressibility, and basically your properties do not really change much in the fluid. Now we learn from forced convection that's not always the case. You know, your viscosity can change, your thermal conductivity can change. So you kind of use to kind of make this stick, this set of equations work, you assume that an average value of all these kinematic viscosity, density, all of these are being evaluated at this temperature called the film temperature, where the film temperature is the the average of the fluid temperature and the surface temperature. Let me break out GIMP in case you'll probably need to have some GIMP. Alright, so testing here. Okay, so this is the fluid temperature. That will be equals to the free stream temperature, plus the surface temperature divided by 2. So just keep this in mind. All your properties are evaluated at this temperature, so you can still sort of think of all of this as a constant. Okay, that's for largely incompressible fluid. Alright, but in natural convection there is some density change in the fluid. Otherwise, how you're going to get your natural convection? So how do we actually deal with this small little change? Okay, so the thing is, compressibility does apply here. How do we deal with this? Okay, in the simplification part. So the way we deal with it, if you remember our mass balance equations, we will have del rho u del x del rho u del y plus del rho u rho w del z equals to 0, and if there's no accumulation of mass within the control volume. Okay, so this is a steady state type equation. Okay, this is a not steady state only. Okay, right. Of course, if you were to do your what do you call that, chain rule or product rule, so you can just do a product rule on all this. So one of them, one side we bring the rho out, the other side we have to bring all the velocity parts out. Okay, so u, v, and w. Okay, so this is how we do this. All right, we do the product rule thing, and one thing we must note. Okay, we got to sort of note is the change in densities. Okay, u del rho del x, v del rho del y, w del rho del z. These three should be pretty small in comparison to this. Okay, these three should be pretty small in comparison to this. Okay, how do we sort of do that? Okay, so let's say, okay, let's divide throughout by this density first, and then we can sort of see a little bit clearer. Or should we? Okay, yeah, let's see the okay, so again we can do some mini scale analysis here. Okay, for example, let's say what is the what is the scale of this del u, right? What's the scale of this del u? Okay, the scale of del u, this will actually go, okay, let's have del u del x, right? This will be equals to delta u delta x. Okay, or at least it scales that way, right? It scales that way. It's on the order of magnitude of delta u delta x. What is the scale of delta u, right? Scale of delta u? Well, the highest it goes is maybe u infinity or the free stream or u max, okay? Some maximum velocity. And this, the minimum will be 0, right? You don't, or it can actually go the other way, okay? If you want. It doesn't really matter that much. And delta x will actually scale, okay? How, okay, what's your dimension like, okay? I forgot to elaborate. Okay, when you talk about natural convection boundary layer, we like to think of this picture. We have a wall here. And it goes up in the positive y direction. Okay, there's this hot wall with surface temperature Ts. It goes up in a positive y direction, and to the right, okay, to the right here is a positive x direction. Okay, to the right is a positive x direction. So you will have fluid at T infinity over here. It will come into contact with the wall, and of course there will be this boundary layer that starts to form, okay, due to natural convection. Because fluid close to the wall will get heated up, and then it will start to rise due to natural convection. So you have movement over here, so you have v velocity, and of course where does the fluid come from? It has to come from the free stream. So u velocity is in a negative direction, right? So this is the picture we are talking about here. So so u max is the maximum velocity, 0 is the 0 is this what do you call that, yeah, length scale, I mean the minimum velocity. And delta x, okay, what is the within the boundary layer, because after all we want our boundary layer equations to describe motion in the boundary layer. Outside the boundary layer in the free stream, we aren't really interested in what the conditions are like. We just assume they are constant, okay? So oopsie. So this is how it's supposed to be. Okay, so what is the order of magnitude of this delta x? This one will be about the thermal boundary layer thickness. Okay, of course you can use the momentum boundary layer thickness as well to non-dimensionalize it, but because this whole flow is driven by this thermal temperature differences, it may be good to, and the underlying reason behind the motion is thermal motion. It may be good to use this thermal boundary layer as this way to non-dimensionalize all your x coordinates. Okay, and of course your y coordinates will be well, if you have a, let's see, I'm going to, okay, this one I can delete, this one I can delete. Okay, maybe I'll just shift it to the side. Yeah, I'll just shift it to the side. Cut, paste, and I'll shift all of this to the side, except for, I'll paste it here. Alright, so again, how do things scale? Okay, over here you will have, okay, I need a nicer color. This color will do. Where's my selection box? Okay, this is embarrassing. Okay, there you go. Alright, in your y coordinate, okay, what's the y coordinate scale? Okay, if you start from this point, this is y equals 0, and then you want to go to, let's say here, okay, we like to call this length h. This height will be called h. So whenever I use the term h to non-dimensionalize y, you will see this is what I'm talking about. How far are we up the wall? in the y direction. Okay, so anyway, okay, so that's del u del x, right, in over here, yeah, the del u del x here. Okay, and del v del y del w del z, or del w del z we can just ignore because we assume 2D. Okay, so let's talk about okay, so this will be on that order of magnitude. Rho will be on what order of magnitude? It will be on the order of magnitude of, you know, maybe rho. Okay, right, so let's see. Rho will just be on the order of magnitude of the density itself, the fluid density. Okay, rho will be on the order of magnitude of rho naught, which is the fluid density at whatever temperature you want. Okay, assuming, and for this derivation, we assume that, you know, pressure changes don't affect rho very much, the density very much. So what's delta rho, right? What's delta rho? What's delta rho? Okay. Oh, sorry. Before that, there'll be this. Let's say you want to have this del rho del y, right? Because we want to check out, you know, what's the temperature, what's the variation in density. Okay, so variation in density, this will scale to be, you know, delta rho and delta y, and of course this delta y, we can say that this scales as h. This delta rho, how much are we expecting? Okay, this one we may expect 0.01 rho, that kind of order of magnitude, and we are not expecting drastic changes in density here. So this is a very small value compared to this. Okay, this rho is a very small value. This delta rho is a very small value compared to this. I'm not going to do all the non-dimensionalization for you now. I'm just hoping to say that, yeah, we can actually sort of ignore all these terms, even though the fluid is technically, you know, slightly compressible. But because these terms are so small compared to the rho over here, we can just neglect them. Maybe 100 times smaller, in fact. Okay, and both these terms are small, but these terms here are smaller than these terms here. That's the point I'm trying to bring across. Okay, so hopefully that convinces you. Of course, you will have v del rho del y, and okay, let me slow down, pause the thing a while. Okay, so yeah, maybe I'm going too fast. Okay, so but let's, yeah, what basically I'll do is a term by term analysis. We do term by term analysis. Okay, so we'll do this a little bit slower in case maybe you miss something. So partial by partial x. So I'm going for this term here, the first term. Partial by partial x of rho. Okay, I'll have this plus rho. Okay, I'll do fraction partial u partial x. Okay, so let's consider the x direction first. Alright, so what am I saying here? Okay, that the scale we are dealing with here, if you want to talk, right? Yeah, the scales that we are dealing with here. Yeah, okay, so let's do the first one, Miniscale. Okay, O. So what's the order of magnitude for the first term? So the order of magnitude of the first term will be maybe some u max. I don't know what this u max is. We'll figure that out later. And then this thing scales delta rho delta x. Delta rho delta x. How does this scale? We need a fraction, maybe 0.01 rho, and then x will be scaling as the boundary layer. Okay, so that's the first term. Plus, okay, so second term, how do we do it? Okay, rho will scale as rho, there's no 0.01 anymore. Okay, Rho will scale as rho. So let me just put the density in front. U max, okay, delta U del U del X will scale as delta U delta X. Okay. So this is how we do the scaling. And of course, this delta U, okay, within the boundary layer, it can vary very close to 0. It can vary very close to the maximum velocity, okay, in the boundary layer. So, okay, now you take a look at this. We can actually just factorize out this, yeah, I mean, most of the terms here are similar. We have rho on both sides. We have delta T on both sides, which is the order of magnitude of this dx, right? And U max over here. Okay, U max over here. So we are not expecting, you know, density to change a lot. How much? What's the number we put in front of this row here? How much does the density change? Well, we'll have to look, you know, by case basis, how much the fluid actually changes density between the maximum and minimum temperature. So for example, water, we don't expect it going from 1000 kg per meter cube all the way down to 500 kg per meter cube. Okay, we don't expect that level of change. Okay, so yeah, okay, water density at different temperature. So just water is the simplest, right? So this is from the engineering toolbox. Let's say we have a 70 degree C plate. Okay, so you see, it's if your ambient temperature is 18 degrees C, you have about 998, right? And then you have a 70 degree C plate, hot plate. So see, 977. So 977. Okay. So what's the change you have here? Okay, 977 minus, or 998 minus 977, something like that. Okay, divide by 998. Okay, so this is about 2% change. It's not negligible completely, but compared to this term over here, you can just kind of strike this thing off. Okay, you kind of just strike this thing off. If you have a 70 degree plate, and then of course your water density changes due to temperature, we won't see very big change. Okay, so we're just going to use that water example. I just put 0.02 here. Okay, so since this change is small compared to what we have here, we can say that this term is approximately just this. Okay, we can just ignore, and we will ignore the first term. This okay, we will ignore the first term. Okay, the change in density term in our continuity equation, even though density changes. Okay, so these are for very small changes in density. So for continuity equation, we will use the incompressible form. Again, for momentum equation, we'll do the same as well, and of course the temperature equation. All right. Yeah. So okay. So this actually deals with the x direction. You can do it for the y direction and z direction as well. Just that in this case, the z direction is not considered. We are considering a 2D flow pattern. Okay, so if you are wondering why while the fluid density changes, we are still using this incompressible form of equations, you can think of, you know, every time you see this density term pop in, it is actually negligible compared to these other terms. So that's the logic that flows when you do this, when you do Navier-Stokes like that. Okay? Yeah, hopefully that clears some initial things up, the setup. So, okay. All right. Let's see. Let's go to the next part, and let's consider other things. Okay. We'll try to start our non-dimensionalization. Okay. Anyway, once we do that, like I said before, we will have our we say the change in density is considered small in comparison to the change in velocity. Well, that's not quite right. I mean, yeah, change in density is small in comparison to, let's say, the to original fluid density. And later on, you'll see us expanding on this assumption in what is known as the Boussinesq approximation. I don't want to overload you too much now, but yeah. So yeah, this is why we are doing it as such. Okay. So bottom line is we are still going to use the mostly incompressible forms of the mass balance equations, which also allows us to use the mostly incompressible forms of the Navier-Stokes equations. Okay, and before I hop on to the next video, I will just want to eliminate all the z direction stuff because we just assume w equals to 0 everywhere. Okay, so we'll just eliminate out the z momentum equations. Okay, so let's go. All right. Okay, we'll get rid of the z momentum equation. So w equals to 0 everywhere. All of these terms will drop out, and of course, gravity in the z direction is 0 because according to what we want, okay, our gravity is only in the y direction. Okay, so I'll stop. Anyway, I'll stop for now. I'll continue more in the next video before I overrun time again.